Can you guys hear me? Good, great. Good morning, thank you for coming. My name is Chen-Si Wang. I'm the Chief Strategy Officer for Twistlock. Twistlock is a security startup in the space of containers, Docker security. How many of you here use Docker or containers? Oh, great. Like 90%, awesome. Sometimes I go to a security conference and it's not that many, that higher percentage that use Docker, so it's great to know that. AppSec is my old stomping ground. I actually keynoted this conference 2010, so it's great to be back. I did a lot of work in the past in application security, and now more on the business side. Dima Stoppel is the VP of R&D in my company, and he's the one who did most of the work. So I'm here just talking about a capability that we do as part of our product, but really is talking about what we can do in terms of on the Linux system to protect containerized applications, actually using the very nature of containers. All right. So I'll do a little bit primer on containers and Docker. I think it's probably too primitive for you guys, but I'll go through that very quickly. Then we'll go into the threat model. What threat model do we address with a system call profiling? And then I'll go into what other things we can do beyond system calls. The example I'm going to use is Nodejs Applications. Obviously, that's a very particular kind of application, but the methodology applies to interpreted languages. So we're going to discuss a little bit what happens if it's not interpreted languages. And then we'll wrap it up and take questions. So by the way, I don't mind questions during the talk as well. So if you have any questions, just raise your hand. And we'll get to that. OK, what is a container? Right? So essentially, I think of containers as user namespaces plus C groups. And those of you who work on Linux, you know namespaces was a concept that was contributed by IBM, I think, largely. Namespaces is the one provides isolation. It basically says, here, this group of processes from the operating system standpoint, you treat them as a unified group. So you can apply a consistent set of rules for that group versus other groups. So if you're a user in one namespace, you kind of don't see processes in another namespace. So that applies to, you got your own networking stack, you've got your own set of users, your process IDs, all those things are isolated from one another. Another concept which was contributed by Google is called C groups. C groups really is there to limit the resources for each group, right? So the resources the operating system can constrain are CPU cycles, memories, and I/O bandwidth, and also provides accounting, which tells you how much of these resources each C group consumed. So with these two concepts, the isolation plus resource constraints essentially make up the most fundamental concept of containers. And think of containers as a lightweight virtualization, and then you put applications inside. This is one of the questions people talk about container come up a lot. I mean, to you guys probably already know, so I will quickly go through it. To your left is traditional VMs. VM virtualize hardware, right? So you've got every guest VM on top of the hypervisor would have its own operating system. So if you use the same operating system, then you're replicating the boot volumes for all these operating systems, and the boot up time and spin down time is much larger than if you were using containers. To the right is containers with Docker engine as an example. For containers, you sit on top of the container engine, and inside the container, you don't carry operating system. So containers, you really virtualize the operating system as opposed to VMs virtualizing the hardware. By virtue of not replicating operating systems or not carrying operating system inside the containers, you use OS as shared resources, so there's efficiency gains, lots of efficiency gains, where you can quickly spin up and down containers, thousands of containers in a second, and also you save a lot of storage. The problem with security everybody talks about is that because you share operating system, so the isolation boundary is different. In VMs, if you have problems with an application, you still have the guest OS to protect you. And here, a compromised application in a container space could conceivably compromise the OS, hence it's called blast radius, hence affect other containers. So we'll talk about that a little bit later. One of the concepts that I'm going to use Docker throughout this talk as an example. Some of the concepts we talk about apply to others, especially on system calls, applies to other container format. But a few things about Docker is really important here. So Docker uses union file system on Linux. And what that means is the inside the container, the different layers are not assembled statically, right? So here we have an example of Debian, Emacs, and it's an Emacs, well, Apache on top. If you have another container on the same host, also use some of these layers, you actually don't replicate the copies on the disk. You dynamically link the same copy for different containers, so there's a lot of efficiency there. Save storage as well. And also, one of the things really important is these layers are typically read-only. Only the top layer, as you can see, is writable, right? So what that means is it allows you to share all these read-only layers because they don't change. And so this container and that container, if they share the same libraries, they essentially share the same bits. And only the top one is unique to each container. So in the past, the top one's actually called container layer. Now they don't call it that much because the whole thing is container. So the thing to really take away from this is containers are largely read-only and immutable. So if you go along, you're executing, you declare statically which layers are going to be in there, right? So you're executing, and you may be writing a few things on top to the top layer. At the end of the session, if you don't specifically do a Docker commit, this image goes away, and the top layer, whatever you wrote there, it goes away. It does not get saved to persistent storage. So there's really interesting security benefit to it, right? So if you are somehow executing and you are saving bad state, if you don't explicitly commit, the bad state goes away. Right? And also another interesting thing is because it's immutable, so there are things you can statically declare or statically determine about the containers that don't change throughout execution. So that's a really, really interesting difference between this and traditional software. All right, any questions so far? So to many of you, this is probably not news, but Docker has seen a tremendous growth. I don't know if you can read the numbers really well. These are the Docker Hub image pools that are in billions. Back in, let's see, I have to read here. I think June 2015, they've got 400 million pools. And November 2015, which is the DockerCon Europe, they had 1.2 billion image pools already. So there's 1.2 billion times people went to Docker Hub and downloaded existing images. And now, I think we're August, we surpassed 5 billion image pools. And in my day-to-day work life, we interface with a lot of enterprise who have either started Docker deployment as a grassroots fashion, and now it's actually moving to using it as an enterprise initiative, and people move extremely fast. So some of the statistic here to the right was published by Datadog. They monitor cloud systems, and they publish statistics once a while for the clients they monitor. 2/3 of those organizations trying Docker end up adopting it. So that's, according to them, that's pretty high. Also, the usage goes up really high. Within the first 9 months of adopting, people tend to go from, say, 1x to 5x within the amount of containers you manage within 9 months. And there's also Datadog also published one other fact is really interesting, that the organizations that are pushing adoption of containers tend to be large enterprise. And you think of enterprise being maybe slow moving, but it's actually not the case in terms of containers. And we see that too, because a lot of our customers actually come from large enterprise. But some of the security challenges come with adopting this new technology, which is primarily driven by developers and DevOps. Lack of visibility, right? Once you put things inside a container, you don't have a way for security ops and DevOps to look into it very easily. There's one of the big thing about containers is portability, right? So developers construct an image, and then you can immediately take it and throw it on a server on AWS or some private cloud and have it executing right there without changing anything, right? So this is the biggest advantage, and what that means is you bypass everything. The developers just do an image and throw it out there. You bypass code review, you bypass testing, and that becomes a really big problem for security operations or security software security professionals. And some of the existing security tools do not work with containers, especially those host-based tools that requires an agent on the software. So think about in the past, like AAV or something, you install an agent on the endpoint, and then the agent collects the information. But AV agent requires update very frequently, right? Think about the container image I showed you earlier. For a container, all the layers inside has to be pre-baked in, right? The minute you construct the image, you say all this library has to be done and not changed. So if I bake a security agent as one layer in the image, throughout its execution session, I cannot change it, I cannot update it. If I do update, I essentially kill the whole image and start up a new one. So no application is gonna want to kill its containers because of a security update. So that becomes a problem. So those things, are becoming more and more emergent in terms of the issues that organizations are facing as more and more applications are moving in containers. So before I go into the methodology of resolving the problem, we'll cover some of the Linux security background to start with, because we'll use these concepts later. How many of you know AppArmor, SE Linux? Yeah, quite a few of you, okay. So essentially, AppArmor is a security module. SE Linux just is an enhanced version in terms of security of Linux. They come with specific functions to prevent access to specific file path, right? So you can, if you look at the top box there, it's a AppArmor specification basically says you cannot access bin dash, cannot access bin sh and bin user bin top, and these methods are forbidden. Once you declare that, and then you run this container with this AppArmor enabled, you try to access these file paths, you'll get an error. Right? So this is one of the ways the operating system provides you functionality to prevent the application from accessing a specific file path. Seccomp is another operating system-based functionality which filters system calls. Right? A seccomp profile, if you enable profile with the application, what it does is basically says, this application, you cannot do certain system calls. How many system calls on modern Linux systems? How many? Come on, somebody. Yeah? It's over 300. So Docker actually comes with its default seccomp profile. If you compile Docker engine with that option turned on, that seccomp profile is already there. And that profile, by default, disallows 44 system calls out of the 300-ish that your application may want to initiate. And that's a good idea to enable those default seccomp. The seccomp profiles is something you can also specify yourself, not just use the default profile. But every time you change it, you have to and re-enable it with your container applications. So there are others. There are other operating system security modules that you may want to use. But for this talk, AppArmor and seccomp are the two that are relevant to us. So let's talk about the container threat model. Right? So it's as we said earlier, you've got parallel containers possibly running on the same host. What kind of threats are possible in this environment? So before we go into the threat model, let's start with some assumptions so we can be on the same page about what threats are relevant. So let's assume that the host is at least configured correctly so that the only way to actually access the operating system is through the applications. So the host does not have superfluous services that's open, listening on a port. You can talk to the host directly because it is a threat, but it's not relevant to containers or not containers. So let's just assume that doesn't exist. Let's also assume that on the host, namespaces, C groups are all functional or enabled. And also, let's assume that inside the container, we have the right software. It's what we intended to use. The software may have vulnerabilities we don't know about, but at least is the one that we intend to use. Okay? So these are the assumptions. So remote attacks. Now, we assumed that the host is configured correctly, so the only way to get to the host OS is through the containers. And so this is a relevant attack, which is remote attack on containers. If this container is talking, has interface that you can remotely access, then you could be looking at DOS threats, remote exploits, or privilege escalation. Some of the mitigations for this, C groups will allow you to limit the resource that a particular container consumes. So it's a way to mitigate DOS threats. It does not solve it, but it does mitigate it. And kernel PID limit does the same thing. And read-only container also, it helps because then you don't change the data from underneath you. These are built-in capabilities from the operating system standpoint. But there are others add on. You could certainly use network security to look at traffic. And there's also, Docker comes with this concept called auth-z plugin. How many of you have tried it or you know about it? auth-z plugin actually allows you to specify fine-grained access control for the Docker environment. That's actually a capability that my engineers have contributed to Docker. And you can do vulnerability scanning to make sure that the software inside the container does not have vulnerabilities, or at least vulnerabilities that you know of before it gets put into containers. And there's also, you could do host-based monitoring as the container is running. So those are the things you could conceivably do to mitigate this threat. Threat model number 2, containers attack the host. right? So let's say the container itself is malicious or has been compromised, or somehow it has intended software, but one of the layers is malware that you don't know about. So it could DOS the kernel, it could do kernel exploits, it could also try to access Docker API that it does not originally have access for. Some of the mitigations, if you remember, we talked about AppArmor and seccomp. So you could enable seccomp to disallow certain system call access, right? Even if there's a malware inside the container, if seccomp is enabled and the operating system has not been compromised, then you would have assurance that certain system calls, they would not have access. AppArmor, certain file system path, a directory they cannot access, and namespaces also help. But those things, later I'm going to talk about, those things are really hard to manage, right? Every time you start a container, you say, oh, here's the profile, seccomp profile. I've written and enable it. But what if you want to change the profile in the middle of execution? Then that's hard. Some of the add-on capabilities, again, OSZ here helps. CIS benchmark assurance, which means that you configured your containers correctly. And you also probably want to do runtime monitoring and threat detection as the containers are running, so you can make sure that it doesn't attack the host. And threat model number 3 is containers attacking containers. So it's fairly similar to containers attacking the host, with the difference that in this threat model, the containers may not necessarily have to compromise the OS. It may just be able to read certain files or certain data of other containers that it didn't previously have access to. And again, the mitigations are fairly similar. You want to do runtime monitoring, making sure your containers are configured correctly, and AppArmor and SE Linux monitoring is turned on. Any questions with these? Yes?
A question about the add-ons. Are they enforced by the Docker engine or enforced by the OS?
These are enforced by the OS. So the question is AppArmor profile, for instance, they enforced by Docker engine or OS. It's enforced by the OS. Docker engine, essentially, it has a default profile that built into the engine. Right? So you can, if you enable that default profile, then the operating system will essentially execute that. Yeah. Question?
Clarify when the OSZ plugin gives you transaction control as opposed to AppArmor or SE Linux?
Right, sure. So that's a great question. The question is, can you clarify the difference between OSZ plugin versus AppArmor, SE Linux? AppArmor, SE Linux is at the lower level. It say, this application executing on OS, what can you access in terms of a file path and seccomp in terms of system calls? It has no notion of users. OSZ is about what users can access Docker APIs. So Docker initially has no fine-grained access control. You as a user, if you can access one Docker command, you can access all Docker command. So for an enterprise, that's hard to do, right? So that means testers will have the same privilege as your developers, as your ops person, which you don't want it to have. So OSZ, so inside the Docker from 1.10, they built in a framework to allow you to differentiate access to different Docker commands. But you have to write an OSZ plugin to tell Docker what to do. So this OSZ plugin basically says, okay, now I want my testing group to do, I don't know, Docker run, Docker PS, but nothing else, right? I want my developers to do, I don't know, Docker remove, Docker run, but nothing else. But the ops people can maybe access 80% of the Docker command. So it gives you a way to say who has which privilege to Docker environment. So that's the difference. Any other questions? So there's actually an open source, we actually wrote an open source RCD plugin to tell you how to do it. It's on GitHub. If you're interested, I can tell you where it is. So the rest of the talk, we're going to be concentrating on threat number 2 and threat number 3. Essentially is regulating the interaction between the containers and the operating system. And I'll tell you why AppArmor and SecComp are not sufficient or not as easy to use. So I've already said this in the past, but it bears repetition to remember. The distinct characteristics of containers that's really interesting for security are 3 things. Containers, if you do it right, is supposed to be minimal. Minimal meaning that inside the container, you should really only implement one dedicated function. You should not take a monolithic application, throw it into containers, and say, hey, I've containerized. You have not done a good job. Right? So assuming it's minimal, which means that one function, one module is inside the container, that's minimalistic. And declarative, meaning that there are a lot of things about the runtime characteristic or runtime constraints are statically declared as part of metadata for the container. And I'll show you later why that is the case. And that is one thing that Docker sort of requires you to do. And we already talked about immutable. All the layers inside the container should be immutable other than the top layer. So those 3 things are really, really interesting for security. So here's an example of a Dockerfile. Dockerfile is basically, you make a Dockerfile when you construct a container, and the Docker engine in runtime processes the Dockerfile and knows what to do with the application. So the top says this image is built from an Ubuntu base image, and that base image is written by this author, right? And then apt-get is, let's do an update dynamically when you run it. Let's do an update of the base image so that we get the most latest library. And then on top of it is a MongoDB. So this is a MongoDB image on top of Ubuntu. And that line there basically says, now go to that location to download the MongoDB library and dynamically build this image for me. Right? And then how to install it and tell you where the default data directory is, if you need to write data or read data. And then the last line says, this is the port you're going to expose. So all these are statically declared as part of the container, and Docker engine will process. But guess what? A security function can also process and understand before you deploy onto the runtime server that these are the things I should expect in runtime. And this is really interesting because in the past, traditional software, I mean, what do you have? You have Makefile. But not much else tells you the runtime constraints. Certainly nothing tells you which port will open easily. So the declarative nature of containers actually is really interesting. It's one that we like a lot because we do a lot with the statically declared data. Now on to this topic that we're here to talk about. So let's start with a very simple Node.js application. So this is basically writing, hello and world and into the buffer, and then you flush the buffer. So with this Node.js is something that you can read it and understand what it is, right? And in runtime, if I run this with a dtrace, it tells me which system call this portion of the application actually uses, which is write, syscall write. But I use dtrace just to illustrate, but you don't actually need dtrace, right? You can look at this and you say, console log, I know console log actually does a write. So that's the system call that this portion of the program is going to execute. And here's another Node.js application, it does a number of things. open a file, write, close, and write to log file. And essentially, I can look at this and I can dynamically say, hey, I know this calls this function, this portion of the program going to execute our open, close, and write. Right? So, and I can write a script to do that. And this is indeed what we have tried in our product. And there are two steps to really decipher what system calls. It's really simple if you think about it. You take a Node.js, you map every API of Node.js to system calls, and you can do that offline, even before you look at any programs. Then you've got this knowledge base, right? And then you see a container image. Inside, there's a Node application, and you do a parser. You write a parser going in to look at all the API calls and map the API to your knowledge base. And now you got a list of system calls, right? And pretty simple, right? And then in runtime, maybe you have a functionality on the server that is observing the system call the application is executing and compare it against the list you have, and you say, hey, how come this application is doing fs get ID or something which is not in my list? Why should it do it? Question?
So I just want to get a little bit of the scale here in step number one. How many APIs are we talking about?
How many APIs? I actually don't know the number. Do you know the number, Michael? How many APIs in Node.js?
No, it's over 15, but I think it's 17.
Okay. It's not a huge number. I thought it was more than that. But it's not a manageable number. Okay. So you can, we've already done this, and you can also do this in your own lab. It's not difficult. Yeah, question?
You mentioned about Nodejs.
Yeah.
APIs.
No. Wait. The dtrace is only, I use it for illustration, right? So we do use dtrace at some point, but for processing Node, here we don't actually need dtrace.
Would we be able to use dtrace to somehow automate step number one? We can run
Yeah. Yes, absolutely. So his observations, you can use dtrace to automate number one. Yes, that's something you should do, and I think my engineers did that. So you can do both steps. You can map the Node.js API to syscalls and do the container image analysis. Both steps before the container ever gets deployed, right? So that's interesting because for security, you kind of know what to expect. And then in runtime, right, you can just say, hey, I've seen this image before because this image has not been modified, and I know this container should have these set of calls, that container should have these set of calls, and then you can load that up as seccomp profile, and then you tell operating system, say, hey, if this container ever does anything outside of that list, block it. You could do that, right? And that's a really interesting thing for application security because in the past, you can't really do that very well or not as definitively, right? And what is the result? The result is you now have a way to whitelist system calls for applications very effectively because it's declarative and because it's immutable. It doesn't change. So that's an awesome result. Yeah? That's a great question. So he asked, is this, are you saying that the list is across all containers or per containers, right? So you want to be per container. Yeah, because every container is going to have its own list of system calls. So you want a distinct profile for each container. Okay? But one of the things that's interesting is, remember I said the containers are layered, layered file system. So you could have, this container maybe have an Apache image as its layer, and that container could have an Apache image as well. Once you've analyzed Apache image, a particular version of Apache image, you don't have to reanalyze again. You know that for this Apache image, here are the list of system calls, then you can just take that and put it in another container and say, oh, this one uses Apache too, so here's the list of system calls. So that is pretty easy to do. All right. Now, there was actually January 2016, there was a 0-day that discovered in the Linux kernel, in a particular version of the Linux kernel, and that's the CVE number. So that's a key control system call, and turns out it has, I think it was a buffer overflow vulnerability in it. And we were able to run this test in our lab using the system call monitoring capabilities that we developed. And it's actually, it's pretty simple because the program that we're monitoring, the key control system call is essentially to create a key ring, and it's only done by applications that would need encryption. And if you don't use encryption, there's no reason to call this system call, right? So we tested out on several programs that we monitor, and we can catch that right away. Now, if you actually are an encryption application using this, then that's get more complex. But if this call is outside your whitelist, you can catch it like that. You don't have to wait for the CVE to come out. So that's a real example. So later I'll get to what happens when the legitimate system call is actually a vulnerable one. Right? But a question that always comes up is, what is the performance hit? Right? So we actually measured this on, I think, an OpenConnect VPN server. I haven't done a lot of tests. In the past, when I was in academia, we would run tons of tests where I'll come with graph, but I haven't done that today, so sorry. With a server that's executing read, send, and receive and write in a very tight loop, and it's fairly fully loaded, and we measure the performance hit on the worker process on the server. All right, so one thing is to understand what system call is being executed. You kind of need to know what system call is. You kind of need to audit that information, right? If you trap every system call, it's really expensive. On a Linux server, sometimes I've measured this in the past, that on a system without auditing turn on, if you can execute, I think it's 50,000 system calls per second. If the throughput turn on audit, it can go down as low as 5,000 system calls per second, right? So that's really expensive. You don't want to do that. So what you could do is you do it sort of offline by using some of the functionality exposed by operating systems, such you can use Netlink to look at networking activities, FN Notify to look at system calls that are relevant to file system. And we measured using this method, the slowdown is less than 1% on this sort of tight loop read-write vanilla server. And second part of performance hit is seccomp, right? So you now audited the system call, and you need to have the seccomp profile in runtime to actually do blocking. And the same server, right? Impact on the worker process is about 2% slowdown. It goes from the throughput goes from 624 megabit per second to 607. So it's not bad. With both auditing and seccomp, it's actually on the order of things is 2% slowdown. If you have a really large program inside, the application could be as high as 3%, but usually 2% is pretty good. Now the question invariably comes is, what if my application is not Node or not the interpreted languages, right? So here's what you could do for the different types of applications. One thing that is really lucky for those that are using containers and for us working in the container spaces, right now it's a fairly contained universe, playing on words, I guess. So you've got interpreted languages, which we already talked about. You can do automated static analysis to extract system call information. For those that are not in the interpreted languages, luckily, today, there are only a limited set of base images that people are using. And you can analyze them fairly quickly and fairly effectively. And again, Datadog reports have listed the top 10 popular images that are people using. Registry, Nginx, Redis, Elasticsearch, MongoDB. MongoDB, I think, is actually not in the top 10 anymore. But these images don't change. They're out there. They may be updated once in a while. So what we've done, and you could do that yourself, is pull all these base images, and there are about 15 of them are probably relevant to you, and you can analyze them. That can be done fairly quickly. And once you've done that, then you can write your seccomp rules or others to protect your application. Now, the more difficult thing comes in when the code is actually custom developed, right? It's not a node, or it's not in the base images, and we call them sort of a Frankenstein containers. And in those containers, what you would want to do is you analyze launch time metadata and combine that with any kind of static information you can determine from Dockerfile, and you do dtrace, essentially. For this kind of thing, you would do dtrace or strace and run it in the sandbox and deduce the system call information. And that is something that we actually is doing the last part right now, but the first two parts are pretty mature already. But on the order of things, what does that mean, right? This is something I'm really excited about as an application security professional who actually have done a lot of work in the past on static analysis. My PhD dissertation is actually a obfuscation compiler, so you can run C source code into the compiler and churn out obfuscated code functionally equivalent. So I spent a lot of my life doing that. But what's interesting is in the past, what we have is software security mechanisms that's looking at code, but we don't really know what the runtime constraints are, what the runtime environment is. And hence, in runtime, we kind of treat the application as a black box. And a lot of the network security rules or even host security rules does not take into account application-specific knowledge. And what this gives me is I can statically process the image and immediately automatically construct a runtime protection policy that goes specifically for this piece of code. And that's really exciting. And this is what we've done in our product is really processing the image for other things, for vulnerability and whatnot. And at the same time, we extract the runtime characteristics, and the policy then is used for runtime monitoring and protection. And you know what this is? This is, in the past, we a lot of application-aware security, like application-aware firewalls and whatnot. This is not application-aware anymore. This is really application-specific policies that you're able to derive, and that's very exciting. But going back to, I don't have a lot of time left, so I'll quickly run through a few of the slides, then we'll take questions. Some of the challenges I said earlier that it's all good when the application is doing something outside the whitelist, right? But what if it is executing the same function, but it's doing something bad, right? So that's the part that I didn't cover. And that does happen. So to take this further, instead of looking at just a list of system calls, what you want is to look at sequence of system calls, right? So if the sequence is anomalous, then you can flag it. And also, you can go a step further by analyzing the parameters of the system call. Then you can say, okay, am I passing the right parameter? Is it too long? Is it too short? Whatnot. So there are some past academic research that was done on different systems. I think one's on Unix. I don't remember what modes was, but these logic we can repurpose to do patterns and parameters. But the more interesting thing is, I talked about system called whitelist, right? But think about the Docker file that I listed earlier. There are other things in the Docker file that you can use to whitelist things. So what else we can whitelist? We can actually whitelist networking behavior. Okay? We can process the image statically and understand whether that image is part of a distributed system, and it's supposed to talk to these 3 containers but nothing else. And also, what port is open, we can know that statically. So if it's suddenly listening on a different port, we'll know. And also file system behavior. So we actually can process the image and know statically whether it's mostly write or mostly read, where it's reading, where it's writing. On launch time metadata analysis, we'll know whether it's mounting a data volume or whether it's talking to a data container. So these things we would know ahead of execution time, which is really, really exciting. Anyway, so I'm running out of time. A very practical consideration, we talked about seccomp and AppArmor, is really difficult to manage. So you can write the rules, you can load up the profile with respect to each containers, but then what if you need to change it? Especially if you need to do this at scale across millions of containers, thousands of servers, which some of my customers are doing. So my recommendation is actually, these are all fine and dandy if you're talking about an individual host or a few hosts you have to manage manually, and you really have to write those rules manually, right? SE Linux is even more difficult to manage. So this is the value that Twistlock provides. This is not a product pitch. I just wanted to compare and contrast some of the existing functionality with this. So we actually manage those rules automatically, and we will process the application image and automatically build a policy, automatically build a seccomp profile for you, and then enforce it. So you, as a application security professional or sysadmin, you don't actually have to write your own, I saw the sign back there. You don't actually have to write your own rules. You don't have to write your own seccomp profiles. We do that all end-to-end for you. So that's one thing that when you have to scale up in an enterprise environment is important. So okay, with that, here's my contact information. So I will take questions here. We have less than 10 minutes, but if you want to contact me for anything else, use that email address. Questions? No questions. Oh, there's a question.
So in a container file, pretty much you have...
You mean Dockerfile?
The Dockerfile.
Yeah.
You have, how complete is it from resource utilization perspective? Whether you can process a Dockerfile and you can extract the list of the process directory that this container can access and utilize those as a basis for policy.
Yeah, so Dockerfile doesn't have everything that you need. I wish it has everything, then you can just go to one place. It doesn't, right? It has certain things that it tells you which library is inside, where you get the library, whether the library is updated. One of the things that you could very easily tell is you can process the Dockerfile and say, oh, this container, this image, if it's instantiated into container, it's actually not using the most updated library because it has no updated pool in there. So you can go back to the developer and say, hey, you need to put that line in there. But other things like resource limits, not typically manifested as part of the Dockerfile. So there are other things you have to do. You have to at launch time, you have to process the application config file to get information from the config file, which is different resource. And you can also, there's also Docker Compose, which is a somewhat new thing, is another declarative file, which in Docker Compose tells you whether this container is part of a distributed application, which other containers are in this distributed application. So that's also a very valuable information to have. So to do this right, you really have to get information from many different resources and put together a comprehensive runtime policy. Yeah, question?
I appreciate the CVE example from earlier this year. Are there other examples of things that this technique is very good about protecting against? I'm particularly thinking about like application errors, not necessarily things in a library. Is it effective against that? Or, I don't know, the sorts of dumb stuff that developers often do of, XML injection or something like that?
Yeah.
Is it
So
effective against that?
it's a very good question. The question is this kind of method is effective against human errors, right? Dumb programming errors. I would say depending on what the error is, right? So what I described here, if you don't look at the parameters of the system call, then it doesn't protect against buffer overflow attacks, for instance, right? We don't process the size of the parameter, or at least what I talk about, it doesn't. But you can add that, right? So I guess the short answer to your question is it depends, and there are always going to be human errors that you're not prepared for. So I'm not here to tell you that we can prevent against all errors. Programmers are very creative. When I went to grad school, I have a team member who loved to declare a underscore as a variable name. That's what he does. And anyway, so that's not a security error per se, but it's just no end of programmer creativity. There was a question there.
So when the platform, supposedly a platform gets compromised and the attacker then starts creating a swarm of these containers.
You mean platform? What platform are you talking about?
The platform which the container runs on.
You mean Docker engine or
Yeah.
the container engine? Yeah.
Container engine. So if the container engine gets somehow compromised and then the attacker starts pulling a swarm of containers, so does it also limit the number of containers? So basically attackers doing anything like pulling bitcoins using that swarm. So
the question is, what if Docker engine is compromised and the attackers can do a lot of things? Yes, but so you sort of look at the different layers. What if the application is compromised? What if the Docker engine is compromised? What if the OS is compromised? If application is compromised, you still have the engine, you still have the OS to protect you. If the container engine is compromised, you still have the OS to protect you, right? So for instance, if you enable C groups as part of the operating system, even if the container engine is compromised, you still would have C group protection, which means that a particular container still cannot exceed the resource limit that's imposed by C groups, because that's part of the operating system. Even the container engine cannot overwrite the OS if you configure it right? So there are certain things, yes, you can do, but OS is there. And this particular talk, we didn't address the threat of what if the container engine is compromised. You can do a lot of things if it's compromised, particularly if the protection capability is pulling information from the container engine, and it can lie to the protection functionality. So those things are for another talk. Other questions? All right. Thank you so much for coming, and let's all use more containers.